A single speck of microwave glow contains the blueprint of cosmic structure. That tiny pattern tells us where galaxies and dark matter later assembled. The early universe looked like a hot, luminous fog with subtle ripples. Those ripples are tiny temperature differences, and they equal density fluctuations. This matters because those tiny contrasts ultimately shaped every galaxy we see. Physics froze those ripples into light as the universe cooled, and we now measure that light. The mechanism is simple at core. Pressure pushed back against gravity, creating standing waves in the primordial plasma. Photons scattered repeatedly until the universe became transparent and the waves froze. Instruments capture the brightness and polarization of that fossil light across the whole sky. For example, the cosmic microwave background shows temperature variations of only tens of microkelvin. Those variations correspond to density contrasts around 1 part in 100,000. So a faint glow holds a precise map of cosmic structure, and we can read it. Quantum jitter was the seed of everything we now call structure. Tiny quantum fluctuations in fields existed even before inflation began. Inflation rapidly stretched space, magnifying those microscopic jitters to astronomical scales. The key point is that quantum uncertainty became classical variations in density. This matters because it links the smallest scales to the largest cosmic patterns. Mechanically, the inflatoned field fluctuated, and those fluctuations set initial curvature perturbations. Space expanded exponentially, freezing modes as they left the horizon. Later, re-entry converted curvature into density variations that gravity amplified. A concrete example is the amplitude of primordial fluctuations near 10 to the -5. The spectral tilt deviates slightly from perfect scale invariance by roughly a few percent. These measurable numbers constrain inflation models directly. Net result, quantum noise stretched by inflation seeded the cosmic web. We detect that ancient snapshot with microwave telescopes in space and on Earth. The cosmic microwave background is ancient light, stretched into microwaves by cosmic expansion. This matters because it carries a direct record of primordial fluctuations. Telescopes observe across multiple frequencies to separate cosmic signal from galactic and extragalactic foregrounds. Detectors sit at cryogenic temperatures to reduce thermal noise and increase sensitivity dramatically. Satellites like COBE began the task, WMAP refined the picture, and Planck delivered high-resolution, low-noise maps. Instruments measure both temperature anisotropy and polarization patterns, which encode different physical processes. An example is how polarization reveals the velocity field at last scattering and reionization signatures later. Data pipelines calibrate detectors, remove systematic errors, and model foregrounds precisely. End result, these instruments turn a faint microwave glow into maps ready for physical interpretation. So careful measurement is the bridge from tiny photons to robust maps. Those sky maps translate into real maps of matter through known physics. Photons interacted with the photon-baryon fluid before decoupling, imprinting acoustic patterns onto the light. This matters because the angular pattern today encodes physical scales at recombination. Mechanically, gravity pulled matter inward, while photon pressure pushed matter outward, creating oscillations. Silk damping wiped out small-scale power, while the finite thickness of last scattering blurred fine details. Transfer functions describe how primordial perturbations map to observed temperature and polarization. Analysts invert that transfer, using Boltzmann solvers to infer initial conditions and later growth. A concrete example is the first acoustic peak, which corresponds to the sound horizon scale at recombination, about 1 degree on the sky. So sky anisotropies carry a scale-by-scale record of early motion, and we can use them to deduce the matter distribution. The power spectrum compresses the map into a diagnostic curve of scale versus power. In plain terms, it measures fluctuation strength as a function of angular scale. This matters because peaks and troughs encode physical parameters like baryon density and dark matter content. You compute it by decomposing the full sky map into spherical harmonics, then measuring variance for each multipole. Lower multipoles probe enormous scales, and higher multipoles probe fine structure. Acoustic peaks appear where oscillations added coherently across the line of sight. The relative heights of peaks tell a quantitative story. For example, more baryons increase odd peak heights relative to even ones. Silk damping causes an exponential-like decay at high multipoles, reducing small-scale power. As a concrete number, the fluctuation amplitude at the scale of 8 megaparsecs is often quoted as sigma 8, roughly around 0.8 in our universe. So the power spectrum condenses complex maps into a readable fingerprint that ties directly to physics. Turning two-dimensional sky maps into three-dimensional matter maps requires surveys and gravitational lensing. Galaxies act as biased tracers of underlying matter, so we must measure their positions and distances accurately. This matters because three-dimensional maps reveal the cosmic web directly and permit growth measurements over time. Mechanically, spectroscopic surveys split light into spectra to measure redshifts and thus distances through Hubble's law. Photometric surveys estimate redshifts from colors, trading precision for depth and area coverage. Weak lensing measures tiny shape distortions caused by total mass along the line of sight, giving a direct probe of dark matter. Combining galaxy clustering and lensing breaks degeneracies between galaxy bias and true matter amplitude. For example, the Sloan Digital Sky Survey mapped millions of galaxies to create a web spanning billions of light years. Modern programs like DES, chi-DS, and Euclid push deeper and wider, improving three-dimensional reconstruction. Net result, these methods transform sky maps into volumetric maps of matter and structure growth. Simulations connect initial conditions to the observed cosmic web by evolving gravity and gas physics numerically. You set initial perturbations with a measured power spectrum and then run gravity on billions of particles. This matters because nonlinear evolution couples scales, and analytic methods cannot capture detailed structure formation. Mechanically, n-body codes advance particles under mutual gravity, while hydrodynamic solvers add gas cooling, star formation, and feedback from stars and black holes. Subgrid models parametrize processes happening below resolution, and calibrations improve realism. Mock surveys extracted from simulations allow end-to-end tests of measurement pipelines and error estimation. A concrete example is the Millennium simulation, which used hundreds of millions of particles to reproduce large-scale clustering. Newer simulations include baryonic physics and produce synthetic skies for comparison with observations. So simulations are essential for interpreting maps and for translating measured patterns into physical understanding. Statistical inference turns maps and simulations into constraints on cosmology and fundamental physics. The idea is to compare data to model predictions and quantify likelihoods of parameters. This matters because maps provide some of the tightest constraints on quantities like matter density and expansion history. Mechanically, analysts build likelihood functions that include observational noise, instrument systematics, and astrophysical foregrounds. They then sample high-dimensional parameter spaces using MCMC or nested sampling algorithms to derive posterior probability distributions. Joint analyses combine CMB, galaxy clustering, lensing, and supernovae to reduce degeneracies and tighten errors. A concrete current puzzle is the Hubble tension. CMB-inferred expansion rates disagree with local distance ladder measurements by several percent. Another example is using combined data to measure neutrino mass bounds, often constraining the sum to below a few tenths of an electron volt. One-sentence recap: robust statistical inference converts messy maps into precise constraints, and sometimes into puzzles that hint at new physics. These maps teach us a lot, yet they point to unknowns worth chasing. We see a universe dominated by dark matter and accelerating under dark energy's influence. That matters because the maps quantify component fractions to surprising precision. The mechanism of discovery is iterative. Better measurements refine models, which guide better simulations and surveys. For example, Planck measured cosmological parameters to sub-percent precision, creating a benchmark model widely called lambda CDM. Yet tensions and large-scale anomalies persist, motivating new missions and experiments. Upcoming surveys like Euclid, the Rubin Observatory, and CMBS-4 aim to reduce errors dramatically and to probe primordial gravitational waves and small deviations from standard models. A concrete payoff would be discovering a signature that discriminates between inflation models or locating physics beyond lambda CDM. Bottom line, tiny fluctuations remain our most powerful window into cosmic origins, and mapping them keeps uncovering surprises.